We work with batch data and we work with streaming data sources. And I think one of the bigger challenges is like, because you want to do a lot of transformations as the data is moving in streaming data, because if you end up collecting the data and then you're just in the batch paradigm, right? But one of the challenges is definitely like, as the data is streaming, how do I join with, let's say, other streams, or maybe even like data that exists in a warehouse, right? Let's just talk about that. Like, why is it challenging, and what can we do?
Yeah, I think that it's actually pretty impressive how powerful the join capabilities are in data warehouses. When you think about what does a data warehouse need to do in order to run a join, the data warehouse generally has files in blob storage, S3, be it Presto or Athena or Snowflake. It's all just data sitting in S3 in files. I want to run a query that does a join between two tables. It needs to figure out how much data is on the left side, how much data is on the right side, rough estimates, and then decide between a bunch of different strategies. Either it's going to do a merge join, in which case it needs to send a unit of data with a range of primary keys, a range of keys for the join to one server, and then another unit of data with a range of keys to another server, and do that, distribute all the data in this fashion, have each server run the join separately, and then continue processing. If you have another join, you might need to redistribute the data again between all the servers. So it's like you're taking the data from S3, you're distributing the data to all the servers, and then redistributing it for each join that's keyed differently. The same, by the way, for an aggregation. You're also going to redistribute the data. That's pretty much what a join is in a data warehouse. And the fact that they can do this quickly on large data sets is super impressive, considering how much data is transferred and how much chatter there is.
Really quickly, because I think you said redistribute. So we're distributing the data twice in two separate steps. What's the second step?
So each time you want to do it, so let's say I'm joining on my user ID. So I'm joining between a table of events and a table of users based on the user ID. So I need to distribute all the events based on a hash of the user ID and all the users based on a hash of the user ID, so that the same user and the events of that user would be in the same server's memory space. Then let's say I'm doing another join based on the country ID. So I need to redistribute based on a hash of the country ID. And then it's reshuffling all the data. And then let's say I want to aggregate based on a couple columns that are not the user ID or the country ID. So now I again need to reshuffle so that a server would have the list of keys that are relevant to that aggregation. So basically each step of the way is going to be a reshuffling of all the data, essentially. That's kind of the strategy of a merge join. And these shuffles are very expensive. Like it's a lot of work kind of to send all the data again somewhere else. And even more so when you're talking about data warehouses, you tend to have a lot of data. They often are going to take advantage of the fact that the data is columnar. So they only send what they absolutely need. They don't send all the data. They send just the columns that are relevant. But still, you have a lot of data going around the pipe everywhere for each join that you do. That's kind of like the standard join strategy. That's what's going to happen most of the time when you join between two equivalently sized tables. The second join strategy is a broadcast join. So basically, in a broadcast join, you're saying, I know that one of the tables is really small. Maybe like it's a reference data table, a couple hundred records, a couple thousand million, whatever, like, but enough that really this fits in memory. And it'll be a lot more efficient to not shuffle the data, but rather I'm going to have a copy of the entire data set on each server. So I have one server load the data, send the data out to all of the other servers, and then I join. Each server can just take whatever data it has and join into that. And that works really well for small data, like up to a few, let's say, up to a few million rows. You can do an effective broadcast join, and that'll be a lot more efficient than sending all the data where where the large table could be a lot bigger than a couple million rows. But you're limited by the memory of the machine that you're using. So at some point, broadcast joins just aren't feasible, and they're going to cause your queries to error out. And again, a testament to the resiliency of data warehouses today is that you don't actually see these errors very often. Like when you're running in Snowflake or in Redshift, you're not really going to see like, oh, I ran out of memory because my broadcast, like it just figures it out and handles it for you. So that's pretty impressive. But this is what's happening behind the scenes, and this is going to affect both your cost and your query performance very heavily. All that is relevant to batch. When we're talking about streaming, you're getting new data constantly. You have new events arriving all the time. And a merge join just isn't feasible because my new amount of data is really tiny. Almost any bigger table that I'm joining into, it's going to be a big process to load in all that data. So really like merge joins become, let's say they become kind of irrelevant because you're dealing with a small batch of data. So kind of by definition, you're going to want to do a broadcast join. But the funny thing is that you also don't want to need to scan all of the data for the join every single time. You have a small batch, it's happening maybe once a minute. Do I really want to scan my large table in order to do this join every single minute? I mean, that's also a lot of expense. In traditional databases, we had indexes. I mean, this is what they did. You would create an index, and then the join is very fast because it goes to a very small section of that data warehouse. And this kind of segues into what Upsolver does in order to solve the streaming join problem, is that we essentially index your data lake. So rather than needing to broadcast join your little increment, but still you need to load all of your raw data, you build an index of your raw data so that when you do the join, you can very efficiently just pull in the data that you need. And there are a lot of optimizations around that, but the let's say the takeaway, the thing that makes this feasible is that you can use a very large index and join into it very quickly. So kind of performance profile of tens of billions of keys in the index, and you can still do hundreds of thousands of join operations per second per server that's running. So it really scales out very, very easily. And that allows you to process a large influx of data, a large data pipe in real time as it's happening without needing to compromise on the size of your join. This is something that's quite unique. So generally, when you're talking about data warehouses, the way you're going to handle joins is you're just going to slow it down. Rather than running every minute or every 15 minutes, maybe you'll join every day. And then it's feasible to scan all your data in order to process the join. Maybe if your data set is smaller, you can do it once an hour. But really, every single time you run your ETL, you're scanning all your data. So you're paying for a full scan of your data every single time. So it really gives you a strong incentive to reduce the speed at which you update your data sets. Whereas in Upsolver, since we're building an index offline that happens once, and then each event gets joined directly, you don't need. It doesn't matter what your flush iteration is, because anyways, each row is going to be joined individually. So you're really not even gaining anything. You may as well write your data every minute or every 15 minutes or whatever kind of the business requirement is, rather than compromising because of cost.
That is so cool. So each event as it arrives is going to get sent to, it's going to get broadcast, and we already have in store in the servers in memory the indexes for the table that we're joining against. Is that right?
Yeah, exactly. So each event, basically, as it comes through, it joins into an index, which is already at least mostly it's going to be already loaded completely into memory for the usage that you want to do. So for the keys that you want, And if not, then it's a very short distance away. So it's not something that's going to slow down your ETL. You don't need to scan hundreds of Parquet files. You're going to need to go to one small block in order to find your data.
If it happens that while the join is happening for one event, a second event arrives, do we have to wait for the first one to be done, or do we time do?
So generally, the way Upsolver works is that it does mini batch, or micro batch. Like it does take a bunch of data and streams it through the pipeline. Now, it still does process the events one at a time. So it is a naturally streaming system. But since we're writing to a data warehouse or things like that, you're dealing in files. So it makes sense to have a file source and a file target and process the events within it one at a time. But that being said, the servers can easily process a lot of different data streams. So you can have multiple sources that you're reading from. You can have multiple chunks or files of data that are processing in parallel, and they're going to share the cache between them. So if you have a lot of ETLs that are using the same state, you're not going to need more memory for that. Very similar to how a database does it, but optimized for data lake scales. So just making sure that all the data is compressed in memory and making sure that that everything is as easy as possible to find, considering that it is sitting in the lake still. It's not, you don't have kind of a local storage like a database, which is a lot more expensive. You're really just going to the lake for your states.
Makes sense. What about aggregations? Or is there an additional complexity for aggregations, or it's pretty similar?
Aggregations and joins are actually pretty similar when you think about it. I mean, both of them require a shuffling step. And then once I have shuffled, calculating an aggregation is it depends on the aggregation, but more or less you need to just scan the data from the key that you're aggregating. So and often depending on the aggregation, often you can do multiple chunks of the same key and then aggregate the aggregated results. So actually, an aggregation and a join from a complexity, let's say from a data warehouse internals complexity, is very, very similar. And also the operation that it ends up doing is very, very similar. It's just what it does with the result set. So you could say that, in fact, I would say maybe an aggregation is easier than a join, because usually for a join, you get 10 records in and you get 10 records out, or 100 records out. Usually a join increases the amount of data that you're dealing with. So after the join step, you have more network traffic, kind of. Whereas an aggregation reduces the amount of data. So from 100 records, you're going to end up with 10 or with 1. So that means that the steps that happen after the aggregation are kind of inherently easier because they deal with less data. So I mean, in Upsolver, again, you can do aggregations as well. I mean, it runs on the same infrastructure that the joins give you. So we pre-compute the aggregations, and I mean, really, you just treat it as a join. You can think of an aggregation as a specific case of a join into a state, which is the aggregate state in this case.
We're not talking about aggregating across an entity in the stream then?
Usually an aggregation in a streaming context has a relevance time window. So that can be infinite. It can be over the entire stream. So I could say, let's say I have a stream of user events, and I want to calculate a simple aggregation like the amount of events per country in this stream. And I want to know that result daily. So I would aggregate over a day, and then each day I want to know how many events happened in that day per country. So the aggregate is on kind of a section of the stream. And the nice thing about it is that since you define the aggregation as part of an ETL, you can actually pre-calculate the results. You don't need to go back each time you want to output new data, because you already scanned it. So you know that in the first 12 hours, there were this many events. Now you get another minute, you just increment everything by 1. So you can hold the internal state there as part of the stream. But then, of course, you could also say, well, I don't want to know per day. I just want to know in total for each country how many events were there, or how many distinct users were there per country. So that's, again, something that you're going to, since you're pre-computing the aggregates in stream time, you can do that very efficiently. And then when you want to output the historical totals, you just take that aggregated state, which is, again, the same state as you would have in a join, and then output that. So it's actually ends up being very straightforward once you have indices in the lake, um, and avoids kind of the full scan every single time you want to output something.
Awesome.
I think that let's say in the streaming context, talking about aggregates and joins, these are kind of the biggest differentiators. It's the biggest reason that people are going to want to do batch instead of streaming is because they want to do easy aggregates and joins, and having that makes streaming a lot more compelling, I think, and it also supports a lot more use cases. It's useful in a lot more cases where this is actually like the business need, and you can't compromise on that really. But on the other hand, you don't want to start building things that are like defining your own aggregations. You still want to just run SQL. So I think this is a huge difference maker in leveling the playing field between batch and streaming, and allowing more users to use streaming systems rather than batch in places where that makes sense.
Great. All right. Thank you for that.